Hello, Prof. Joe here. Today we're going to expand on our knowledge of impulse and momentum by looking at the principle of linear impulse and momentum for a system, looking at the conservation of linear momentum, and also looking at impact, where this topic is very beneficial for solving problems. So let's go ahead and get started. I wanted to start off with just a little reminder of what we learned in the last video. We were able to use Newton's second law to derive the principle of linear impulse and momentum. And what that told us is if we have a single particle and we start off with a momentum and then apply a force, we have a final momentum. So we start with an initial momentum, mv1, and then a force acts over time to change the momentum, and we end up with mv2. Well, the question we're going to look at in this video is what happens when we have more than one particle. You have a collection of particles, as I can see over here. I've got a bunch of blue dots. And I also have a few forces. In this case, I have two forces acting on two of those dots. Well, if we look at that system, we could write an equation where we're just going to sum up all the forces and use Newton's second law. The sum of those external forces acting on the system, and external will be very important when we get to impact, the sum of those external forces is going to be equal to the sum of all of the changes to their momentums. Okay? So if we find each momentum individually of each particle and figure out how they change, that has to be proportional to the force. If I put dt on the other side and I integrate, same steps I did in the last video, I can come up with a very similar equation, which is the principle of linear impulse momentum. As you can see, the main difference is we're taking a collection of parts over here, the sum of the mass of each component and the velocity of each component for our initial momentum, and then we're summing up all our forces for our impulse, and then we're summing up our final momentums. So you could look at this as just solving a whole bunch of momentum equations simultaneously, or you can look at it as a system. And there's a real benefit to looking at it as a system because we get to choose our systems. And in doing that, we'll be able to choose what is external and internal to our systems. So what do I mean by that? Well, let's think of this. We have these two particles and they move. They had a change in momentum. Did our system also have a change in momentum? Well, let's look at that. If we set this up as a system, all these particles and this white background, I'm just saying these are all together. And we think of a fictitious mass center. The idea that if we summed up all of the masses and the distances they were from an arbitrary point, we could do a weighted average and figure out where is the mass center of this collection of points. And then if we move our forces again, we apply our impulse just to two of those particles, what happens? Well, our mass center moves because of the motion of those particles. So we have actually given momentum to our entire system. What momentum were we given? Well, it's equal to the impulse. And we can have a very similar equation to linear impulse momentum where we have mvg1, where vg is that fictitious mass center, plus that impulsive force over time is equal to the momentum of our fictitious mass center at the end. Okay, so basically I've just told you so far that we can use this equation for a collection of parts. How is that useful? Well, it really comes in handy when we're looking at a system without external forces. In this case, we have a system with some particles on it, and let's say it's moving. It has an initial momentum, okay? And then we have two particles inside of that system hit each other and move. Did the momentum of the entire system change? Well, you have to ask yourselves, was there any external forces to our system? No. In this case, there were no external forces to our system, and so our impulse comes out of the equation. So our linear impulse and momentum equation gets a heck of a lot simpler. That comes out and we end up with an equation called the conservation of momentum, where if we sum up the momentum before the collision and the momentum after the collision, we can, those are going to be equal to each other. Most of the time when we use this equation, we're using it over a very, very small time period. Think of two pool balls. And if we look at those pool balls as they're coming towards each other, and we make a system just a millisecond before they hit and a millisecond after they hit, if we do that, we can actually find the velocity that we expect them to leave without worrying about the forces between them. Let's see how that works. We're going to be talking about impact, and we want to define impact first. Impact is when two bodies collide over a very short period of time, creating large impulsive forces. You can see a video of a golf ball hitting some steel at a high speed, and you can see that this takes place in a very small amount of time. If we were trying to calculate that force so that we could do a sum of the forces equals mass times acceleration, that would be very challenging, right? We'd have to have very good sensors, and those sensors might be knocked out because of those high impulsive forces. But if we instead looked at it as a change in momentum, we could come up with an easier way to solve it. There are two types of impact we're going to look at in this class. The first one is central impact. In a central impact, you have one or more particles that are going to impact each other along the line that connects their two mass centers. Here's an example. Two particles just going towards each other, hitting each other and bouncing back. If you were, at the instant that they hit each other, if you were to draw a line connecting the two mass centers, the impact would be right along that line. Okay? That's the more simple impact, and we're going to figure out how to solve those problems and then build upon that for the second type of impact, which is our oblique impact. Oblique impact just means that they're impacting at an angle that does not match a line drawn between their two mass centers. For example, these two particles are hitting each other and bouncing off. They're still, the line of impact is still defined as a line that goes between the two mass centers at the instant they hit each other. So the line of impact is still defined the same way. The plane of contact is perpendicular to the line of impact. And we still have those two things, but they're not always going to be as easy to find. So how are we going to solve these problems? We actually have to look into deformation a little bit. We are in rigid body mechanics, which means we shy away from deformation most of the time. In rigid body mechanics, we pretend like things don't deform so we can calculate approximations of reality. In this case, with high impulsive forces, we have to look into deformation and use it to our advantage. And you can see another golf ball hitting some steel here. And as it hits the material, it's going to start deforming. That first deformation, there is some energy taken out of it. And with the restitution, we get some of that back. So as it deforms, there is a lot of force over a very short period of time, and then it will come back to shape. Now, by definition, we can't get all that energy back because some of it's lost in the sound that you hear, some of it's lost in permanent deformation of the material, so we're not going to get it all back, but we're going to get some of that energy back. So by definition, our integral of p dt, which is our deformation force, is going to be greater than our integral of r dt, which is that restitution force. Okay? So that's always going to be greater. But depending on the materials, we can come up with a quantity called the coefficient of restitution. And the coefficient of restitution is going to be that restitution force over the deformation force. And you can actually look these up for different materials. For example, you can look up a coefficient of restitution for steel on glass or for steel on steel. And you can get some quantities. Two that you should know about would be E equal to 1. If you get E equal to 1, that means we're getting all of the energy back. That is only a theoretical impact because it will never happen in real life. And in that case, we call that an elastic or fully elastic impact. On the other extreme, we have a coefficient of restitution equal to 0, and we call that a fully plastic impact. Okay, and real materials are always somewhere in between this, somewhere in between 0 and 1. To give you some more typical values, If you're looking at wood on wood, you get somewhere between 0.4 to 0.6. If you look for steel on steel, you get somewhere between 0.5 and 0.8. So the harder the material, the higher the coefficient of restitution. Lead is somewhere like 0.12 with impact. So you can find these values and they can help us solve the problems. If you have an object coming in about to hit the wall and you need to solve what's the velocity when it comes out, we need to know the coefficient of restitution. And then what we do is we say, well, the coefficient of restitution is going to be equal to the velocity of one particle, we'll call that VA2, minus VB2 over VB1 minus VA1. This gives us one equation to help solve for the velocities of impact. If this is an impact of a golf ball against a wall, as you see over here, that would be enough. We'd be able to find the velocity of the golf ball after hitting because we'd only be solving for one velocity, right? The velocity of body 2 would be the velocity of the wall, and the wall's not moving. So we'd have a 0 here and a 0 here. We'd know the velocity coming, the initial velocity coming in. We'd be able to solve for the initial velocity coming out. When you have two particles, such as two balls hitting each other, you need another equation. And you're going to use the conservation of linear momentum. That equation just says the sum of all the masses times all the velocities initial is going to be equal to, and that's a vector, all the masses, the sum of all the masses times the velocities final. So if you know the velocities of both particles before, and you know the coefficient of restitution, then you can find, using this equation, are two unknowns, which would be the velocity of one particle after and the velocity of the other particle after. But those equations only work for a central impact. Remember, a central impact was when two particles impact along a line that connects their two mass centers. For oblique impact, you have to actually set up two different coordinate axes. You have to pick your coordinates so that you can split it up into a central impact problem and conservation of momentum. How do we do that? Well, you can see over here, we have to first find the line of impact. Draw a line between the two mass centers right at impact. That is your line of impact. And call that the x-axis. Once you have that x-axis, along the x-axis, which is the line of impact, you're going to use those same two equations, the coefficient of restitution, which is going to be equal to the velocity of one of the particles after minus the velocity of the other particle after, over the velocity of the second particle before minus the velocity of the first particle before. Notice how we change order. We change order because that will give us a positive coefficient of restitution. If A was going faster, if B was going faster than A before, after the impact A will be going faster than B. So we have to flip them in order to get a positive number. Make sure that you keep them in that order. Along the x-axis, you're going to use this equation and also the conservation of linear momentum equation. And you'll be able to solve for the velocity in the x direction after for both of those. Okay, but that's only going to be your velocity in the x direction. Along the y-axis, which is your plane of contact, there's no contact happening. Perpendicular to the line of impact, there's no contact happening. So the velocity of one particle in the y before, which is generally known, will be equal to the velocity of that same particle after. And same exact thing for the second particle, the velocity of b, y, before equals the velocity of By after. Velocity is conserved because along that axis no impact is happening. You will often have to take a velocity that's known, tilt your coordinate system, separate it out into its coordinates so you know which of those is along the line of impact and which of those is perpendicular to it. And then you can solve oblique impact problems. Make sure to take a look at the example problems that are also posted in this playlist. Please let me know if you have any questions.